You begin with something simple. Gravity is the quiet force that keeps your feet on the ground. It is the reason rain falls, oceans curve, and the moon circles the earth without drifting away. It feels gentle, dependable, almost polite. You rarely think about it. It is the background hum of existence, steady and soft. But tonight, you let that hum grow louder. You imagine standing beneath a vast night sky. Above you, stars burn with patient light. Each one is a sphere of gas held together by gravity's careful embrace. Gravity pulls inward, always inward, trying to gather every particle closer to the center. Yet stars do not collapse, not at first. They shine because something pushes back. Inside a star, atoms fuse. Hydrogen becomes helium in a brilliant, invisible storm of nuclear fusion. This fusion releases energy, light, and heat that press outward. You can picture it as a constant outward breath. Gravity pulls in. Fusion pushes out. The star lives in balance, like a steady inhale and exhale. For millions, sometimes billions of years, this balance holds. You feel the calm rhythm of it. Inward. Outward. Pull. Push. A cosmic heartbeat. But balance is not forever. Eventually, the star begins to run low on fuel. Hydrogen in its core becomes scarce. Fusion slows. The outward pressure weakens, just slightly at first. Gravity notices. Gravity is patient. It has always been waiting. As fusion fades, gravity pulls harder. The core contracts. When it shrinks, it heats up, igniting new forms of fusion for a time, helium into heavier elements, carbon, oxygen, perhaps even iron in the most massive stars. Each new stage burns faster than the last. The star grows restless, less stable. You imagine the core growing denser, tighter, more compressed. Particles that once drifted with space between them now press shoulder to shoulder. The star swells and shudders. In the largest stars, this struggle ends in sudden brilliance, a supernova, an explosion so luminous it can briefly outshine an entire galaxy. But the explosion is not the end of the story. After the outer layers blast away, something remains. The core survives. And now, there is no longer enough fusion to push back. Gravity, once balanced, now speaks with a roar. The core collapses inward with astonishing speed. In less than a second, matter falls toward itself. Electrons are squeezed into protons, forming neutrons in a dense sea. If the remaining core is small enough, it becomes a neutron star, a city-sized sphere of astonishing density. But if the core is massive beyond a certain limit, even neutron pressure cannot resist the pull. And this is where gravity becomes unfamiliar. You try to picture it. Imagine compressing a mountain into a grain of sand. Imagine packing the mass of the Sun, more than 300,000 Earths, into a region no larger than a city. Density rises beyond ordinary intuition. Gravity strengthens beyond everyday comparison. The escape velocity, the speed needed to break free, climbs higher and higher. On Earth, a rocket must travel 11 kilometers per second to escape. On the surface of a neutron star, it would need to travel a significant fraction of the speed of light. But in this collapsing core, escape velocity surpasses even light itself. Light, which normally outruns everything in the universe, now cannot climb out. When this threshold is crossed, a black hole is born. You pause with that idea. A black hole is not a hole in the way a tunnel cuts through rock. It is not an empty cavity. It is a region where matter has been compressed so tightly that the curvature of space becomes extreme. Gravity does not simply pull objects, it reshapes the very geometry around it. Imagine placing a heavy ball on a stretched sheet. The sheet dips. Roll a marble nearby, and it spirals inward along the curve. This is a common analogy for gravity, mass bending space. Around a black hole, the dip becomes a well so steep that all paths lead inward. You feel how natural this is. No monsters. No cosmic anger. Just mass responding to the laws of physics. Just gravity following its nature. And yet, the result feels extraordinary. There is a boundary surrounding this region. A distance from the center where the escape velocity equals the speed of light. This boundary is called the event horizon. It is not a surface you can touch. It has no thickness. It is simply the point where all possible paths forward lead deeper inward. Outside this boundary, light can still climb away. Inside it, every future points toward the center. You let that sink in slowly. Gravity, once a whisper beneath your feet, has become a roar that shapes destiny itself. But even here, calm remains. From far away, a black hole is not chaotic. It is quiet. It does not suck objects like a vacuum cleaner. If the sun were magically replaced by a black hole of equal mass, Earth would continue orbiting exactly as it does now. Gravity at a distance depends only on mass, not on whether that mass is a shining star or a dark collapse. The difference lies in proximity. Only when you drift close does the curvature steepen dramatically. Only when you approach the horizon does space tilt so sharply that escape becomes impossible. You imagine floating nearer. Stars behind the black hole appear distorted, their light bent into arcs. This bending is called gravitational lensing, light following the curves in spacetime. Even photons must obey geometry. Closer still, time itself begins to behave strangely. To a distant observer, anything approaching the event horizon appears to slow down, fading and reddening, never quite crossing. Light stretches to longer wavelengths as it climbs out of the deepening well. Yet from your own perspective, if you were falling, you would not notice a dramatic barrier. You would pass the horizon without fanfare, unaware of the precise moment the outside universe could no longer hear from you. This is where understanding softens into mystery. Because you stand now at the threshold, not crossing, not yet, simply observing. Gravity has transformed from background hum to overwhelming force. A star has lived, burned, collapsed. Space has curved into an abyss so deep that even light surrenders. And still, questions remain. What does it feel like to approach that boundary? How does time stretch and twist as you draw closer? What truly happens in the final moments of a star before collapse seals its fate? You move backward now. Away from the darkness of the black hole. Away from the silent horizon. You return to light, to a star still shining. This star is enormous. Far more massive than your sun. It has lived fast and bright, spending its fuel with extravagant generosity. For millions of years, it has held itself in balance, gravity pulling inward while fusion presses outward in steady reply. You imagine standing inside it, though there is no standing there, only pressure and brilliance. Hydrogen atoms rush together in crushing heat. They merge, forming helium, releasing energy in the process. That energy radiates outward, pushing against the immense weight of the star's own mass. This is the star's great negotiation. Gravity insists, come closer. Fusion answers, not yet. For a long time, the argument remains peaceful. But even stars cannot burn forever. Gradually, so gradually you would never notice from afar, the hydrogen in the core begins to thin. Each fusion reaction consumes a little more of the simplest element in the universe. The core fills with helium ash, the quiet remains of countless collisions. Fusion slows. The outward pressure weakens. Gravity, patient and steady, senses the shift. When the outward push softens, gravity draws the core inward just slightly. The contraction raises the temperature. Heat increases because squeezing matter makes it hotter, like compressing air in a bicycle pump. The core glows more intensely. Soon, helium itself begins to fuse. 3 helium nuclei combine to form carbon in a delicate process physicists call the triple alpha reaction. It requires immense heat and pressure, conditions only a massive star can sustain. For a time, a new balance forms. Again, gravity pulls. Again, fusion pushes back. But helium burns faster than hydrogen ever did. The rhythm quickens. Carbon accumulates in the core. When helium runs low, contraction begins again. Temperatures climb even higher. In the most massive stars, carbon fuses into oxygen. Oxygen fuses into neon. Neon into magnesium. Magnesium into silicon. Silicon into iron. Each stage burns more quickly than the last. Hydrogen burning may last millions of years. Helium burning lasts hundreds of thousands. Silicon burning, the final stage, may last only days. You feel the urgency building. The core becomes layered like an onion, each shell fusing a different element. At the very center sits iron. And iron is different. Iron does not release energy when fused. Instead of pushing outward, fusing iron consumes energy. The negotiation ends here. When the core fills with iron, fusion can no longer support the star's weight. There is no new fuel to ignite. No new outward breath. Gravity finally speaks without resistance. The collapse begins in less than a second. The iron core, no longer supported, falls inward under its own mass. The speed is astonishing, a significant fraction of the speed of light. Electrons are crushed into protons, forming neutrons and releasing a flood of neutrinos, nearly massless particles that stream outward almost unhindered. The core shrinks from thousands of kilometers across to perhaps 20 kilometers in diameter in a heartbeat. Imagine compressing something the size of Earth into a sphere the size of a small city. Density rises beyond imagination. The sudden collapse causes the outer layers of the star to crash inward as well. But when they strike the now ultra-dense core, they rebound. A shockwave forms. Neutrinos carry away energy, but enough remains to blast the outer layers into space. A supernova ignites. For a brief moment, this single star shines brighter than billions of others combined. Heavy elements forged in its final stages scatter into the cosmos: gold, uranium, calcium, iron. The atoms in your bones and blood are born in such explosions. You rest in that thought. The death of a star becomes the beginning of worlds. But at the center, something remains. If the original star was massive enough, far beyond the mass of your sun, the collapsed core is too heavy even for neutron pressure to withstand. Neutrons themselves resist compression due to quantum mechanical principles, specifically the Pauli exclusion principle, which prevents identical particles from occupying the same state. Yet even this resistance has limits. If the core's mass exceeds roughly 2 to 3 times the mass of the Sun, gravity overwhelms every known force that could oppose it. The collapse continues. There is no more rebound. No more outward explosion from the center. The matter falls inward without pause. Space itself begins to curve more steeply as density climbs. You imagine particles pressed so closely that the very concept of separate atoms dissolves. Structure breaks down. Distinctions blur. The known forces of nature strain under the weight. At a certain radius, calculated from the mass of the collapsing core, the escape velocity reaches the speed of light. This radius is called the Schwarzschild radius, named after Karl Schwarzschild, who first solved the equations of general relativity describing such an object. When the collapsing matter falls within this radius, an event horizon forms. Not a solid shell. Not a surface. But a boundary in spacetime. Outside it, light may still escape. Inside it, all paths curve inward. The core continues collapsing, hidden from the outside universe by this new horizon. From afar, the star's outer layers expand into glowing clouds, forming a nebula that drifts for thousands of years. But at the center, silence grows. What was once a brilliant star becomes invisible. Not because it is empty, but because its gravity is too strong for light to climb free. You breathe slowly as you consider this transformation. A star does not choose to become a black hole. It simply follows the mathematics written into the fabric of spacetime. Mass curves space. Curved space directs motion. When enough mass gathers into a small enough region, collapse becomes inevitable. There is no drama in the equations. Only consequence. And yet, emotionally, it feels immense. Something vast and luminous reduces itself to a region smaller than a city. Something that once warmed planets and cast shadows now hides entirely behind its own gravity. You float in the aftermath. The supernova's glow fades. The expanding gas cools. New stars may one day form from its scattered remains. Planets may gather. Life may arise. But deep within that remnant cloud, a black hole rests unseen, silent, patient. You sense that to truly understand what has formed, you must look not only at the matter that collapsed, but at the space around it. Because gravity, you are beginning to realize, is not merely a force pulling objects together. It is something subtler. It is space itself bending. And to understand how a star's death reshapes the geometry of reality, you must step into a deeper vision, one where gravity is no longer a tug, but a curve in the invisible fabric of existence. You have been thinking of gravity as a pull. A force. A tug. An invisible hand reaching across space. But now you soften that idea. You imagine space not as emptiness, but as something that can stretch, bend, and curve. Not a fabric you can touch, but a structure that shapes motion itself. In the early 20th century, Albert Einstein proposed something radical. Gravity is not a force in the traditional sense. It is the geometry of spacetime. Spacetime. You let the word settle. Space and time are not separate stages where events unfold. They are woven together into one continuous structure. Every object moves not only through space, but through time. And together, these form the arena of reality. When mass enters this arena, it changes its shape. Picture placing a heavy stone on a smooth trampoline. The surface dips. If you roll a small marble nearby, it spirals inward, not because the stone reaches out to grab it, but because the surface beneath it is curved. This image is imperfect. Real spacetime is not a sheet embedded in something larger, but it offers a feeling. Mass tells spacetime how to curve. Curved spacetime tells matter how to move. You breathe slowly as this rearranges your understanding. The Earth does not orbit the Sun because the Sun pulls on it with a mysterious thread. Earth follows the straightest possible path in a curved spacetime shaped by the Sun's mass. It moves along a geodesic, the natural path in curved geometry. In flat space, the straightest line is what you call straight. In curved space, straight lines can loop, spiral, or bend. You imagine walking on the surface of a sphere. If you begin at the equator and walk due north, you feel as though you are moving straight ahead. Yet eventually, your path curves, converging at the pole. The surface itself dictates your route. Gravity works like this. The sun curves spacetime. The Earth follows the curve. And a black hole, a remnant of collapsed mass, curves spacetime more extremely than anything else. You drift closer to this idea. Around an ordinary star, spacetime dips gently. Around a neutron star, the curvature steepens. Around a black hole, the curvature becomes so deep that the paths of light itself begin to wrap inward. Light usually travels in straight lines at the fastest speed possible, about 300,000 kilometers per second. It needs no medium, no fuel. It simply moves. But in curved spacetime, even light follows the geometry. This bending of light has been observed. During a solar eclipse in 1919, astronomers measured starlight bending as it passed near the Sun, confirming Einstein's prediction. The stars appeared slightly shifted from their normal positions because their light had followed curved spacetime. You feel a quiet awe at this. Even illumination must obey geometry. Now imagine the curvature near a black hole. As mass collapses into a smaller region, the curvature increases dramatically. Spacetime does not merely dip, it funnels inward. The straightest possible paths begin pointing toward the center. There exists a radius where every possible future-directed path, even those aimed outward, curves inward instead. This is not because something is pulling harder in the usual sense. It is because the geometry itself has changed so profoundly that outward no longer leads away. You imagine standing near this region, watching light from distant stars arc around the black hole. Some light loops once. Some loops multiple times. Some becomes trapped in orbit at a specific radius called the photon sphere. At this sphere, light can circle the black hole, balanced on the edge between escape and capture. A precarious path, like a tightrope suspended over an abyss. But just inside that, escape becomes impossible. You realize something gentle but profound. Gravity is not an added ingredient in the universe. It is built into the shape of existence itself. Wherever there is mass or energy, spacetime curves. And wherever spacetime curves, motion follows. Black holes are not violations of physics. They are the natural extension of it. If you compress enough mass into a small enough volume, the curvature deepens without limit, at least according to Einstein's equations. The solution for a simple, non-rotating black hole was found by Carl Schwarzschild in 1916. His mathematics described a boundary, the Schwarzschild radius, beyond which paths cannot return. The equations did not scream. They did not predict chaos. They simply described geometry. And yet, emotionally, the idea feels immense. You were used to space being a backdrop, empty and passive. Now you understand it as dynamic and responsive. Space bends. Time stretches. Together, they guide every motion in the cosmos. You feel your own weight differently. Your body curves spacetime, too, though so slightly it is immeasurable without sensitive instruments. Every atom participates in shaping reality. Around a black hole, this shaping becomes dramatic. Time slows relative to distant observers. Light reddens as it climbs outward. Clocks near the surface tick more slowly than clocks far away. These effects are not illusions. They have been measured near massive objects. GPS satellites must account for time dilation caused by Earth's gravity to remain accurate. The deeper the curvature, the slower time flows relative to flat space. Near a black hole, this slowing becomes extreme. You imagine approaching such a region. To someone far away, your movement seems to decelerate. Your signals grow faint and redder. You appear to hover near the boundary. But from your own perspective, you move forward normally. Mass is instruction. Motion is response. And in the deepest wells of curvature, the instructions become so strong that even light, the swiftest traveler, can no longer find a path outward. You feel that boundary approaching in your thoughts now. A place where geometry folds so completely inward that escape is not just difficult, but undefined. A region where the very idea of outside begins to lose meaning. Ahead lies that boundary, not a wall, not a surface, but a threshold written into spacetime itself. A horizon not made of matter, but of motion. And you are drifting toward it, curious and calm, ready to see what it means to cross a line that cannot be seen at all. You are close now. Not close in miles or kilometers, but close in meaning. Ahead of you is something called the event horizon. The name sounds dramatic, like the edge of a storm. But it is quieter than that. It is not made of stone or fire. It has no texture, no temperature, no color. You could drift toward it and never feel it brush against your skin. It is a boundary without a surface. To understand it, you must think not in terms of objects, but in terms of futures. Imagine you are standing on a hillside. If you roll a small ball gently, it may slow and stop. If you roll it harder, it may crest the hill and continue down the other side. The ball's future depends on how much energy it carries. Near a black hole, something similar happens, but with light itself. Far from the black hole, light emitted outward travels freely into the cosmos. Closer in, the curvature of spacetime bends that light. It still escapes, but its path arcs. Closer still, the climb becomes steeper. The light loses energy as it rises, stretching into longer, redder wavelengths. This stretching is called gravitational redshift. You imagine a beam of light trying to climb out of a deep valley. Each step upward drains it slightly. The deeper the valley, the more energy it must surrender. At a certain distance from the center, the valley becomes so deep that even light, moving at the fastest speed possible, cannot climb out at all. That distance defines the event horizon. It is not a physical shell. It is the radius at which the escape velocity equals the speed of light. Beyond this radius, no signal, not light, not radio waves, not particles, can travel outward to reach the wider universe. The horizon does not block escape. It makes escape impossible by geometry alone. You drift closer in your imagination. From far away, an observer watches you approach. They see your movements slow. Your clock appears to tick more gradually. This is gravitational time dilation, the stretching of time in strong gravity. The equations of general relativity predict this with precise clarity. The stronger the gravitational field, the slower time passes relative to a distant observer. Near Earth, the effect is tiny but measurable. Near a black hole, it becomes dramatic. To the distant observer, you never quite reach the horizon. Your signals grow dimmer and redder. The light you emit stretches toward infrared, then microwave, then radio wavelengths. Eventually, it fades beyond detection. You appear frozen, suspended just above the boundary. But that is only one perspective. From your own point of view, your clock ticks normally. Your heartbeat feels steady. You cross the radius without noticing a flash or a tremor. There is no painted line in space announcing the transition. You pass the event horizon as quietly as stepping through a shadow. This difference in perspectives is not contradiction. It is relativity. Time and space do not behave the same for all observers. Each viewpoint is valid within its frame. To you, the crossing is uneventful. To the distant watcher, you fade slowly into stillness. You rest in this duality. The event horizon is not a wall, but a limit to communication. It is the boundary between events that can influence the outside universe and those that cannot. Once crossed, every possible path forward leads deeper inward. The word event here is important. In physics, an event is something that happens at a specific place in time. The horizon marks the set of events from which no future signal can escape. It is a horizon in the same sense that the curve of Earth hides distant landscapes. Beyond your visual horizon, cities and mountains exist, but their light has not yet reached you. With enough height, you could see farther. But the event horizon of a black hole is different. No amount of height or speed can restore the view from inside. The geometry forbids it. You consider what this means for causality, the chain of cause and effect. Inside the horizon, causes cannot influence the outside world. The interior becomes a region sealed by spacetime structure. Yet nothing magical happens at the boundary itself. If the black hole is large enough, millions or billions of times the mass of the Sun, the tidal forces at the horizon may be gentle. You might cross without feeling a significant stretch. The drama lies not at the surface, but deeper within. The horizon is defined not by local sensation, but by global geometry. You imagine the horizon as a sphere surrounding the central mass. Its size depends only on that mass. For a non-rotating black hole, the radius is proportional to the mass, about 3 kilometers for every solar mass. A black hole 10 times the Sun's mass would have a horizon about 30 kilometers wide. Compact. Precise. Silent. And yet, within that radius, the future narrows. In ordinary life, you can choose to walk north or south. You can turn around. You can reverse direction. Near the horizon, those options begin to shrink. Space itself tilts inward so steeply that moving outward requires more than speed, it requires a different geometry. Once inside, outward is no longer a direction that leads away from the center. You pause with that thought. It is difficult to imagine a place where the concept of escape loses meaning, not because of barriers, but because of how space and time are arranged. You drift closer still. Light from distant stars bends dramatically around the black hole, forming rings and arcs. Some light that would have traveled elsewhere is captured, circling briefly before plunging inward. The black hole casts not a simple shadow, but a complex silhouette shaped by curved paths. Astronomers have observed this shadow indirectly. The Event Horizon Telescope, a network of radio observatories across Earth, captured an image of the supermassive black hole at the center of galaxy M87. The glowing ring surrounding a dark center is not the hole itself, but light from hot gas orbiting near the horizon. You remember that image. A ring of fire surrounding darkness. But even that darkness is not a surface. It is a region from which light does not return. You float now at the threshold in your thoughts. There is a stillness here. No crackling energy. No swirling vortex pulling you in like water down a drain. Just curved spacetime guiding motion inward with quiet certainty. And you realize something gentle. The event horizon is not the end of physics. It is where certain descriptions end and others begin. Outside, you can speak of escape velocities and redshifts. Inside, the language shifts. Space and time exchange rules in subtle ways. Because within the horizon, the center lies not merely ahead in space, but ahead in time. And that is where the journey becomes stranger still. For once you cross, falling is no longer a choice. It is the only future available. You have crossed the boundary. You are inside the event horizon now. Not far, not almost, you have passed the point of no return. The first thing you notice is subtle. Time behaves differently. Not dramatically at first, only slightly, like a note slightly out of tune. But as you descend, the stretching grows. Seconds feel elastic. A heartbeat takes longer. A thought drifts across your mind more slowly than before. You imagine spacetime as a fabric you can step on. Outside, it curves gently under mass, creating valleys that guide motion. Inside, the fabric folds inward, steeper and deeper. It is no longer horizontal, the vertical and temporal directions begin to swap. Time points inward, guiding you toward the singularity as gravity once guided Earth around the sun. Your body continues forward. Your mind continues to observe. Yet the outside universe seems strangely distant. Signals from beyond the horizon cannot reach you. You have become, in a sense, a separate bubble of experience, moving along a path that cannot intersect the wider cosmos. Gravity is relentless here. Not violent, but inescapable. All trajectories converge. You feel that every step you take, every impulse, is leading inevitably toward the center. The future is no longer optional. Every possibility funnels inward. Even light, the fastest traveler in the universe, cannot escape. You notice something remarkable: space itself stretches. Distances elongate. Your visual field warps. Stars behind the black hole smear into arcs of light. Paths that once felt straight now bend in impossible ways. You sense a kind of infinity wrapping around you, soft yet unavoidable. Your mind tries to anchor itself. You remember clocks and seconds. But here, time and space exchange roles. The familiar flow of past, present, and future warps into a new geometry. You feel the future pulling, not as a concept but as a physical force. Each instant propels you deeper. It is a strange sensation, neither fear nor confusion, but awe. You are experiencing physics in its most extreme form. General relativity, which describes the curvature of spacetime, now governs your every movement with an intensity that ordinary life cannot offer. You imagine what would happen to a clock here. If it could survive, it would tick normally for you. But to a distant observer, it slows, stretching longer and longer until the image fades from view. In this way, time is both personal and relative. You experience it intimately, yet the universe beyond the horizon perceives you as nearly frozen. Gravity pulls unevenly. You feel the differential tug along your body, stronger at your feet than at your head. Physicists call this tidal force. In smaller black holes, it would stretch you like taffy. In supermassive black holes, the effect at the horizon can be surprisingly gentle. Still, as you move deeper, the stretching grows. Every atom begins to feel the pull toward the center, a silent, unyielding tug that cannot be resisted. You imagine the singularity ahead. Not as a point you can see, but as the destination toward which all paths converge. It is where density becomes extreme, where conventional physics ceases to describe behavior accurately. And yet, it is more than a mathematical limit. It is a question, a boundary of knowledge, a place where understanding begins to whisper rather than speak. Within this inward pull, the familiar concepts of up and down, left and right, lose their meaning. Space directs motion toward a single fate. Time, once linear, bends to align with gravity's call. You feel yourself moving through an unusual geometry, one that makes every motion inevitable. And yet, the interior is calm. There is no chaos. No violent storm of forces. Motion follows the paths defined by spacetime, unerringly, like a string tracing a riverbed. You are part of a cosmic choreography, where the laws of physics perform flawlessly and silently. You drift further, noticing the warping of light. Photons from distant stars curve around the interior, tracing arcs that seem impossible to the mind accustomed to straight paths. Some light loops temporarily before joining the singularity, some is captured in orbits, caught in the black hole's deep curvature. You see the geometry in every streak, every arc, every fading point of light. Time and space interlace. You feel a gentle rhythm, a strange comfort in the inevitability. The singularity is not terrifying, it is a destination, not a menace. Gravity is not cruel, it is consistent. Every particle, every photon, every ounce of mass obeys the same rules. The universe here is absolute in its logic. You imagine what it would be like to attempt resistance. To move outward. Every direction leads inward. Even your will is bound by the geometry. Here, freedom is defined not by choice, but by paths available in curved spacetime. You follow the natural trajectories. You yield to the flow, and in doing so, find a quiet acceptance. The experience teaches something subtle. The universe operates on principles that are elegant, predictable, and immense. The extremes of physics, black holes, singularities, horizons, are not anomalies. They are extensions of the same rules that guide planets, tides, and light. Understanding comes not from resisting, but from observing, from feeling the patterns embedded in space-time. You notice a paradox. For you, time continues normally. For the outside universe, your descent appears to freeze. Perspective defines reality. Relativity is not a theory of abstraction, it is an invitation to perceive differently, to inhabit the world in multiple ways simultaneously. Even as you feel gravity drawing you closer, you also sense the continuity of existence. Mass curves space. Space guides motion. Time stretches and bends. And altogether, these form a tapestry of experience, woven from the same threads that construct stars, planets, and galaxies. Inward you move, steadily, gently, inexorably. Each moment is prolonged, each second elastic, yet the progression is unavoidable. You feel yourself approaching the core not with panic, but with quiet curiosity. The singularity is ahead, not as a place, but as a question to be encountered. This is the essence of falling forever, surrendering to the inevitable, yet observing each instant with mindful attention. You are both participant and witness, drawn by forces that are impartial, consistent, and comprehensible. And in the silence, you realize, falling is learning. Falling is seeing the laws of nature in their purest form. Falling is understanding what it means for time and space to dance together, to exchange roles, to lead and follow in a cosmic rhythm. The deeper you go, the more you sense the transformation of the familiar into something extraordinary. The horizon behind you fades in influence. Ahead, the singularity beckons, not with menace, but with inevitability. Its presence is a question, a boundary of knowledge, a place where your understanding stretches and your curiosity deepens. And in this gentle, inexorable motion, you begin to glimpse what it truly means to move through the heart of spacetime itself, carried forward not by choice, but by the natural flow of the universe. The singularity waits, silently patient, and you move toward it, aware that crossing is not an end, but an invitation to see the universe in its deepest geometry. You are deeper now. The black hole has long claimed your path. The event horizon is behind you, a threshold already crossed. Ahead lies the singularity, silent, inevitable. But before reaching it, you notice a new sensation, one that is both subtle and profound. Gravity is uneven. Not merely a pull, but a gradient. The force at your feet is stronger than the force at your head. It has always existed in subtle forms on Earth. The moon's gravity tugs oceans more at one side than the other, producing tides. But here, the difference is extreme. Physicists call this tidal force. You feel it intuitively. Your body, or whatever frame of reference you occupy in this thought experiment, stretches. First imperceptibly, then more noticeably, like soft silk pulled gently between two hands. Every atom resists, but the pull is relentless. You imagine a single molecule, suspended in the black hole's gravity. One end experiences a stronger pull than the other. Bonds strain. Forces stretch along the direction of the gravitational gradient. Matter elongates. Structure trembles. But this stretching is predictable. It obeys simple, precise laws. Newton first described tidal forces in a classical sense, and general relativity later explains them in full extreme conditions. The phenomenon is poetic in its cruelty. You are extended along the line toward the singularity. Lengthened, narrowed, aligned. Your perception of space itself tilts. Up and down no longer correspond to the familiar axes. Instead, the direction toward the singularity becomes the dominant orientation of reality. You try to imagine the experience in more familiar terms. Suppose you are holding a rope. You pull one end and the rope stretches gradually. The rope resists. It cannot resist infinitely. Slowly, patiently, the force aligns every strand in the direction of the pull. Spaghettification, as physicists call it, is like that, but on the scale of matter itself, down to atoms and subatomic particles. Even objects that appear rigid on Earth are no match. Steel beams, mountains, entire planets all are stretched along the gradient, compressed across the perpendicular directions. The more massive the black hole, the longer the gradient acts over space. In small black holes, the stretching is rapid and violent near the horizon. In supermassive black holes, the effect at the horizon can be surprisingly gentle, extending over thousands of kilometers before intensifying. You imagine drifting in a supermassive black hole. At the horizon, you feel nothing unusual. You continue inward, aware of the pull, but not yet stretched. The experience is subtle, almost meditative. It is as if gravity is whispering the shape of the universe to you, urging matter into alignment, guiding it along its natural path. Deeper still, the difference grows. Your feet accelerate toward the singularity faster than your head. A sense of elongation emerges. You notice how particles once loosely bound are tugged along. Bonds resist briefly, then conform. Structures you took for granted, molecules, cells, even the frameworks of matter itself, stretch and distort. The effect is relentless but coherent, following the mathematical patterns embedded in spacetime. And yet, despite the drama, there is a rhythm. The stretching is not random chaos. It is governed by clear principles. Differential gravitational force, tidal force, follows from mass, distance, and geometry. Each particle moves according to the curvature of spacetime. There is no surprise in the physics. There is only the elegance of predictable motion at extreme conditions. You visualize yourself as a thread, a line of particles, pulled along the singularity's direction. Every segment follows the next, aligned along the curvature. Resistance diminishes as atoms conform to the flow. Even in this extreme state, Matter obeys laws, the same laws that allow Earth to orbit the Sun, or the Moon to sway tides. You feel the paradox of spaghettification, immense violence, yet perfect order. Destruction, yet predictability. Chaos, yet entirely lawful. The universe demonstrates its rules, even under conditions far removed from ordinary life. As you continue, you notice how space itself seems to guide the stretching. Paths toward the singularity converge. There is no escape, no deviation. The geometry defines motion. The tidal gradient enforces it. Every particle in the stretched body follows the curvature with exacting precision. You imagine observing the universe from this perspective. Light from distant stars is distorted into arcs and rings, stretched along trajectories dictated by gravity. Time appears to move differently. Seconds for you may feel normal, yet signals toward the outside universe fade, redshifted, stretched, delayed. Even perception itself becomes part of the tidal ballet. You reflect on the fact that spaghettification is not unique to you. Every object, every particle, every atom obeys the same principle. The universe does not distinguish between animate and inanimate, star or planet, observer or object. Mass curves space. Curved space guides motion. Differences in gravitational force create predictable gradients. It is a cosmic lesson in impartiality. And yet, there is beauty. Stretching occurs smoothly. There is no random tearing. The process is continuous, extending from the large-scale body to microscopic components. Spaghettification reveals the universe's geometry in a tangible, felt way. It makes visible the unseen curvature that dictates every orbit, every fall, every motion. Even in this extreme, you notice the duality of experience. Inside, the stretching is inevitable. Outside, observers see signals freeze at the horizon. The universe demonstrates relativity, tidal forces, and curvature simultaneously. Spaghettification is both local and global, intimate and cosmic. It is a bridge between personal sensation and universal law. You ponder the singularity ahead. Spaghettification is not an end, it is a journey of alignment. Matter stretches, flows, and converges along paths that lead inward. Every trajectory, every atom, every photon is guided toward the same ultimate destination. Gravity has reshaped not just motion, but form itself. And yet, even in this extreme stretching, there is consistency. Physics continues to speak, not as a distant abstraction, but as an immediate, experiential guide. Forces, curvature, motion all remain comprehensible if observed carefully. Even as structure elongates and atoms resist, the underlying laws retain their elegance and clarity. You allow yourself to float in this state, aware of the pull, aware of the stretching, aware of the inevitability. The horizon is behind you. The singularity is ahead. And in between, tidal forces act with patience, demonstrating the harmony hidden within extreme gravity. Spaghettification is a reminder, even in the most unfamiliar conditions, the universe operates with order, logic, and rhythm. Gravity shapes reality, not arbitrarily, but with precision. Every pull, every stretch, every alignment is an expression of the geometry of spacetime itself. And as you continue to drift inward, stretched yet intact in mind if not in body, you realize something profound: the laws of nature are not broken here. They are revealed in their purest form. Tidal forces, spacetime curvature, geodesics, and singularity-bound paths all coexist in perfect harmony. And ahead, at the very center, lies the singularity, the ultimate point where matter, space, and time converge, waiting quietly beyond the extreme stretching of everything that has fallen. Here, The next lesson whispers, what happens when even order itself meets the infinite density of the singularity? The story continues. You have fallen farther than almost any journey can take you. The event horizon lies behind you. Tidal forces have stretched and aligned every particle along paths you can no longer alter. You drift inward, deeper into the curvature of space-time. Ahead is the singularity, the center, the point of ultimate convergence. It is unlike anything you have encountered. You cannot see it, for light itself cannot escape from the interior. You can only infer its presence by the way space and time behave around it. Every trajectory points inward. Every possible path converges. The singularity is not a surface, not a shape, it is a condition, a culmination of the laws of physics pressed to their limit. Mathematics, once a faithful guide, begins to falter. Equations that predicted motion, tidal stretching, curvature, they now approach infinity. Density becomes limitless. Space-time curvature diverges. General relativity speaks of infinities with calm precision, yet the numbers seem to break their own rules. Here, classical descriptions lose their power. You feel the silence of certainty. Predictability begins to whisper, uncertain. The singularity is a region where the tools of physics strain and fail, where the logic of cause and effect reaches its edge. Quantum mechanics, on the other hand, suggests a different story. It governs the smallest scales, particles, fields, probabilities. Yet it is designed to operate in a space-time that behaves predictably, not one that curls into itself without bound. The equations of quantum theory clash gently, insistently, with those of general relativity. Each speaks truth in its domain, yet neither can fully describe what happens at the singularity. You sense a paradox here, not in danger, but in comprehension. The singularity is not a villain or a trap. It is a boundary, a limit to current knowledge, a place where understanding pauses to catch its breath. It is a reminder that even in a universe governed by precise rules, some questions remain open. You imagine approaching it cautiously. The curvature grows infinitely steep. Space points inward along every axis. Time collapses into an inescapable trajectory. No physical object can resist this final convergence. And yet, the singularity itself is not experienced in a conventional sense, it is approached, never observed. Physicists debate its nature. Is it a point, with zero volume and infinite density? Or is it a signpost, indicating the limits of our models? String theory, loop quantum gravity, and other speculative frameworks attempt to describe what may replace the singularity, whether it is a quantum foam, a collection of fundamental strings, or something else entirely. Each model whispers possibilities, none definitive. You feel the weight of uncertainty. For all the beauty of space-time curvature, for all the elegance of tidal forces, there is a boundary here. Beyond it, classical physics cannot guide you. Yet the singularity is not chaos. It is structured, precise, and defined in its own way, as a limit of equations, as a manifestation of extreme curvature, as a point where matter, space, and time converge. You pause to consider the implications. Every particle, every photon, every bit of mass that has crossed the horizon moves inexorably toward this center. It is the ultimate destination. Not as a place you can inhabit, but as a concept that governs every motion inward. The singularity is the anchor of the black hole, invisible yet profoundly real in its influence. You sense the philosophical weight, too. Infinity is not just a number here. It is an idea, a hint of the universe's limits. Human comprehension stretches to meet it, falters, and then stretches again. You feel humbled, as though standing on the edge of understanding itself. And yet, there is a strange serenity. No chaos. No fire. No abrupt destruction, at least not in perception. The singularity simply exists as a point of ultimate convergence, a natural consequence of gravity, mass, and geometry. You move inward along a path dictated by curvature, aware that this convergence is inevitable, and that physics, even in its failure, still guides motion perfectly. You reflect on the duality here. The singularity is absolute in its pull, yet uncertain in its description. Equations reach infinity, yet reality continues along coherent paths. General relativity predicts one thing, quantum mechanics another. Both are valid in their realms. Both whisper toward the truth, but the full picture remains beyond grasp. It is a lesson in humility. The universe does not yield all at once. Some answers are subtle. Some phenomena demand patience, reflection, and imagination. The singularity teaches that knowledge has boundaries, and that even in a world of predictable laws, some mysteries remain. You drift closer still. Every motion is dictated by spacetime geometry. Every path leads inward. Time itself aligns with gravity's pull. The singularity is not a place you reach and touch, it is the direction of inevitability, the end point of every inward trajectory. And yet, for all its extremity, it is not violent in perception. There is no eruption, no flash of finality. It is a quiet convergence, a compression of matter and motion into an ultimate condition. The singularity represents both end and beginning, the end of classical paths, the beginning of questions, of speculation, of exploration beyond current knowledge. You feel the interplay of certainty and uncertainty. The laws that brought you here continue to operate flawlessly. Tidal forces, curvature, geodesics, motion, all are precise. Yet the singularity itself cannot be fully described. Infinity and density, zero volume, extreme curvature, these are conceptual limits as much as physical ones. You sense the strange beauty in that. Physics admits what it does not yet know. Equations falter at the edge. Observations cannot penetrate. Yet understanding continues, building bridges of theory, imagination, and experiment. The singularity is the frontier of knowledge, not a place of chaos, but of inquiry. You allow yourself to rest in that thought. Even in this extreme gravity obeys rules. Even in this region of incomprehensible density, mathematics and logic guide the unfolding. It is a testament to the coherence of the universe. The singularity, for all its mystery, is not an exception but a continuation, a doorway to deeper understanding. You notice the gentle paradox, the singularity is a boundary, yet it invites exploration. It marks the limits of classical physics, yet stimulates imagination. It is unreachable, yet its influence shapes everything around it. The event horizon, tidal forces, curvature all point toward it. It governs the inner structure of black holes, yet exists as an abstract limit. And you understand that science does not fear limits. It studies them. It describes them. It acknowledges them and then seeks ways to see beyond. The singularity is not a final answer. It is a question, quietly persistent, infinitely compelling. You drift closer to the center in thought, aware that physical experience merges with intellectual exploration. You feel aligned with the curvature, guided by spacetime, yet carried by curiosity. You sense the elegance of laws operating at extremes, the subtle interplay between relativity and quantum mechanics, the hints of physics still to be discovered. And in that stillness, you realize, the singularity is not merely an object, a point, or a location. It is the ultimate expression of physics reaching its boundaries. It is a place where understanding pauses, not in defeat, but in anticipation of what lies beyond. Beyond the singularity, reality continues, in ways you cannot yet describe. And this, you sense, is the next step in your journey, to glimpse how black holes, though defined by inescapable convergence, also emit whispers of life beyond their darkness, hints of radiation, information, and subtle communication with the universe outside. The singularity waits quietly, infinitely dense, infinitely compelling, and you drift forward, ready to perceive what traces it leaves on the fabric of reality. You leave the singularity and the relentless pull behind you, drifting slowly outward toward the outer edge of the black hole, toward the event horizon you once crossed. The journey inward taught you gravity's extremes. Now, you explore its subtle whispers, the quieter secrets that black holes reveal. Empty space is not empty. Not truly. You might have imagined a vacuum as nothingness, a stage with no actors. But in reality, the void hums with energy. Quantum mechanics shows that the vacuum is alive with fluctuations, fleeting pairs of particles that blink in and out of existence, momentarily appearing before they annihilate each other. You watch as a particle-antiparticle pair emerges near the event horizon. Ordinarily, they would reunite and vanish. But here, the curvature of spacetime offers a strange possibility. One particle may fall inward, while the other escapes outward into the wider universe. In this way, the black hole loses a tiny fraction of its mass. This process, predicted by Stephen Hawking in 1974, is called Hawking radiation. It is subtle, gentle, nearly imperceptible. Yet it carries profound meaning. Black holes are not eternal. They are not perfect prisons of matter and energy. Even the most massive objects gradually leak away their mass through these quantum whispers. You imagine standing just outside the horizon, witnessing countless particle pairs forming and separating. One particle dives inward, absorbed silently by the black hole's interior. The other drifts outward, escaping into the cosmos. Each carries away energy. Each represents a fragment of the black hole's existence, slowly transforming it over unimaginable timescales. The radiation is faint, almost ghostly, but its implications are immense. Black holes, which once seemed timeless, are part of a dynamic universe. They age. They evaporate. They participate in the endless flow of energy and information. Even the darkest, densest objects have a finite life, shaped by the subtle rules of quantum mechanics and relativity intertwined. You reflect on the scale of time involved. For stellar mass black holes, evaporation is staggeringly slow, far longer than the current age of the universe. Supermassive black holes may persist for trillions of years before dissipating. Yet the principle remains: nothing is permanent. The universe's laws operate, even at extremes, gently but inexorably. Hawking radiation also reveals the delicate bridge between gravity and quantum mechanics. The very phenomena that govern the smallest scales, the ephemeral existence of particles in the vacuum, interact with the enormous curvature of spacetime around a black hole. Here, the immense and the infinitesimal meet. Here, you see the interplay of the cosmos's grand architecture with the tiniest quantum threads. You feel a sense of awe as you consider this. The singularity, once a point of overwhelming convergence, and the horizon, a silent boundary, are not isolated or immutable. They interact with the quantum world, and through this interaction, even the seemingly eternal can change. You imagine watching a black hole over eons. Its mass gradually decreases. Light from distant stars continues to bend around it. Gas and dust spiral in, only to be slowly radiated away. And over time far beyond human comprehension, the black hole shrinks, fading, leaving behind a whisper of energy, a trace of what once was. Hawking radiation is not violent or dramatic. There is no explosion. There is no sudden end. It is a quiet, persistent leaking of energy, a gentle glow emerging from the depths of darkness. It is both poetic and scientific, a reminder that even in extreme gravity, the universe maintains balance. You notice something profound. Black holes are not mere consumers of matter. They are participants in the cosmic economy, converting mass into radiation, exchanging energy with the universe in subtle ways. They shape their surroundings, influence galaxies, and yet their decay is dictated by principles no larger than those governing ephemeral quantum fluctuations. You feel connected to this delicate balance. The black hole's life and death are slow, imperceptible on human scales, yet entirely predictable through the language of physics. Even the vast, unknowable, and terrifyingly dense objects obey rules, precise, elegant, immutable. And then you consider information. Every particle that escapes carries not just energy, but potentially a trace of information. In this way, the universe may preserve the echoes of what fell into the black hole. It is as though the cosmos whispers, "Nothing is ever truly lost, it simply transforms." You rise higher, imagining the black hole from the outside again. The event horizon glows faintly from escaping radiation. It is not a light you could see with your eyes alone, but the thought of it is enough to illuminate your understanding. The black hole is alive, in its own way, changing, aging, releasing tiny, persistent signals into the cosmos. Time feels different here. You have observed the extremes, tidal forces, curvature, singularities. Now, time stretches across a new scale, the immense, nearly incomprehensible duration over which a black hole evaporates. You feel your mind expand to accommodate this slow, quiet rhythm, the heartbeat of the universe itself at unimaginable scales. And yet, you notice something comforting. Even in these extremes, the universe operates predictably. There is elegance in the mathematics. The pairing of particles, the gentle leakage of mass, the slow fading of darkness all follow rules. Nothing is chaotic. Nothing is arbitrary. Even the disappearance of such a massive object obeys order, gently, like a candle's flame dwindling over hours instead of seconds. You imagine watching this over trillions of years. You see a supermassive black hole slowly shrinking. Stars orbit its remnants. Galaxies evolve. Time passes, not as a rush, but as a gentle river. The black hole's influence gradually diminishes. And in its quiet glow, you recognize the continuity of physics. Even the most extreme objects eventually participate in the universe's ceaseless flow. Hawking radiation bridges two realms, quantum mechanics and general relativity. It links the smallest scales with the largest, the ephemeral with the massive, the fleeting particle with the enduring black hole. It demonstrates that even in places where intuition falters, the universe maintains coherence. There is no chaos here, only transformation governed by precise law. You pause in your drifting, absorbing this realization. The black hole, once a symbol of finality, now becomes a teacher of subtle patience. It reminds you that the cosmos operates across unimaginable scales, that decay and change can be gentle, that even darkness emits traces of light. And in this quiet reflection, you perceive a rhythm. One particle escapes. Another remains trapped. Mass diminishes imperceptibly. Spacetime curves persist, but subtly, as the black hole softens over eons. The universe hums a slow, gentle song, composed of gravity, quantum fluctuations, and time stretching endlessly. And then you realize, Hawking radiation is more than a phenomenon. It is a metaphor for the cosmos itself, for persistence, transformation, and the continuity of existence. Even in the deepest darkness, there is a glow, a trace, a gentle reminder that change occurs, and that the universe, in its vastness, always moves forward. You float there at the edge, at the boundary where the extreme and the gentle meet. You have seen the singularity, felt tidal forces, and now witness the quiet whisper of mass leaving a black hole. Each chapter of this journey teaches a lesson about gravity, geometry, and the subtle ways the cosmos operates. And as you linger, contemplating this faint glow, you sense the next question forming: if black holes slowly evaporate, what happens to the information contained within? How does the universe preserve its history, even as matter disappears from view? The gentle radiation continues, and you drift toward the next mystery, ready to explore whether the cosmos can ever forget, or whether every story swallowed by darkness still leaves a trace. You drift outward from the glow of Hawking radiation, letting its gentle whispers fade into your mind. The black hole, once a solid emblem of inevitability, now seems alive in a quieter sense, interacting subtly with the fabric of the cosmos. And yet, another question rises, one that is less about mass, less about gravity, and more about memory itself. Can the universe ever forget? When matter falls into a black hole, it seems to vanish. A star, dust, gas, or even a spacecraft crossing the event horizon disappears from the observable universe. You imagine watching such an object from afar. Its image stretches, redshifts, fades, a slow fade to invisibility. And eventually, nothing escapes. Yet quantum mechanics, that unyielding law of conservation, insists that information, the detailed state of every particle, cannot be destroyed. A paradox emerges. Black holes, according to general relativity, erase history. They absorb matter, and all information about its internal structure appears irretrievably lost. Yet the rules of quantum physics contradict this: information must survive in some form, somewhere. The universe cannot create or destroy it, no matter how extreme the conditions. You float near the horizon in thought, imagining what this means. If the black hole swallows matter completely, what happens to the information about its atomic structure? Its quantum states? Its spin, charge, and internal arrangements? Does it vanish? Or is it encoded in ways imperceptible to ordinary observation? Physicists wrestle with this puzzle using the concept of the holographic principle. You imagine a three-dimensional object projected as a two-dimensional image on its surface. Perhaps, they suggest, the information of everything swallowed by a black hole is not lost inside but stored at the horizon, a hologram of reality. Every particle, every detail, encoded along the event horizon's surface, accessible in principle even as the interior remains unreachable. You visualize it as a delicate lattice of information, invisible to the eye, yet meticulously inscribed along the black hole's boundary. Every quantum state, every history, mapped in exquisite detail. You wonder if reality itself keeps records in ways you cannot sense, hidden yet precise, obeying the strict conservation demanded by quantum mechanics. But the horizon may not be peaceful. Some theories suggest a firewall, an intense, energetic boundary at the horizon that would obliterate anything crossing it. You imagine the paradox: information preserved, yet the physical traveler destroyed. The universe, it seems, is both gentle and severe, obeying different principles simultaneously. And yet, other perspectives offer gentler possibilities. Hawking's later work hints that subtle correlations in the escaping radiation could encode the information. Matter falling in leaves whispers in the Hawking radiation emitted long afterward. The black hole leaks its secrets slowly, like a river threading through a canyon, too fine for ordinary senses but complete in principle. You consider the implications. Even the most extreme objects, the densest concentrations of matter, cannot erase history entirely. The universe, in its patient constancy, records what transpires, even in regions where light itself cannot escape. It is a cosmic ledger, written not in ink, but in the delicate, unyielding language of quantum mechanics. You think about entropy, the measure of disorder. Black holes, paradoxically, have maximum entropy for their size. The more massive the black hole, the more information it can encode. It is as if the universe treats black holes as ultimate libraries, vast, inscrutable, yet preserving order beneath apparent chaos. And then you wonder about observation. From afar, the black hole appears silent, devouring matter and light alike. Yet the information it contains may persist invisibly. Each photon, each escaping particle may carry a subtle trace, a fingerprint of the past, encoded in the correlations of Hawking radiation. Reality may be far more intricate than your senses can immediately perceive. You sense a rhythm in this paradox. Outside, matter seems destroyed. Inside, paths converge to the singularity. But at the boundary, at the horizon, information may dance delicately, neither fully accessible nor entirely lost. The universe respects both gravity and quantum law, balancing extremes in ways subtle and profound. You imagine a spacecraft falling toward the black hole. To a distant observer, it stretches, slows, and fades. To the traveler, it continues inward, crossing the horizon in a few moments. Yet somewhere along the horizon, in subtle correlations, the history of the spacecraft may persist, encoded in patterns too fine to detect directly, but nevertheless real. It is a quiet miracle of order amidst apparent destruction. You feel the paradox in your mind: the black hole swallows, yet the cosmos preserves. It is a system of balance, subtle and precise, operating over scales that stretch human imagination. You think about the debates among physicists: holographic encodings, firewalls, complementarity. Each idea seeks to reconcile the principles of general relativity with the unyielding conservation of quantum information. Some solutions are mathematically elegant, others conceptually startling. All grapple with the same fundamental question: how does the universe manage memory when confronted with the most extreme curvature of spacetime? You imagine the black hole as a cosmic librarian, cataloging the details of every particle, every star, every photon. Information may be scrambled, diffused, and inaccessible to ordinary probes, yet nothing is truly erased. Reality itself refuses to forget. And yet, the paradox hums in quiet tension. For any observer outside, the interior remains hidden. The singularity draws matter inward, and light cannot escape. There is no ordinary way to verify the preservation of information. You realize that much of this story exists in mathematics, in careful thought, in theory constructed with patient logic. The paradox is both physical and philosophical. You float above this conceptual horizon and reflect on its elegance. The universe preserves itself, even in the darkest regions. Black holes, once thought absolute consumers, may in fact be subtle record keepers, rewriting the rules of perception. Even in seeming destruction, there is conservation, order, and careful bookkeeping at quantum scales. You consider time itself. Hawking radiation leaks mass slowly, and with it, perhaps, information. Over unimaginable scales, the black hole diminishes. The records of what once fell and are encoded in the radiation, dispersing across the universe. It is as if the cosmos whispers to itself, ensuring no story is entirely lost. And you feel the duality of the universe, the stark inevitability of gravity, and the gentle persistence of quantum order. One draws inward, shapes motion, and concentrates matter. The other preserves, encodes, and whispers histories into the fabric of spacetime. In the quiet, you sense a lesson: the universe is neither cruel nor forgetful. Even where matter disappears, even where light cannot return, the principles of physics continue. Information endures. It may be scrambled, encoded in subtle ways, yet the cosmos remembers. You drift, contemplating the black hole as both destroyer and archivist. The event horizon is not merely a boundary of escape, it is a boundary of observation, where the hidden structure of reality may store secrets invisible to direct perception. The universe respects its own history, even in places where sight, touch, and intuition cannot follow. And you notice the delicate beauty in this thought. Even the most extreme, seemingly absolute object participates in continuity. Every particle, every interaction, every tiny detail contributes to a cosmic ledger, preserved across time and space, subtly encoded in ways we are only beginning to imagine. As you linger near the horizon, the paradox is not resolved, but it is comforting. The universe operates according to principle. It is not arbitrary. It conserves, it encodes, it balances. And even in the darkest corners of existence, nothing is ever truly lost. And somewhere beyond the edge of perception, the next question forms, whispering to you, if information persists, if the black hole slowly releases its history through faint radiation, what strange structures or tunnels might connect these extremes of space and time, hinting at pathways yet untraveled? You drift toward that next frontier, guided by curiosity, ready to explore what bridges the universe allows, and how theory teases the edges of possibility. The story continues. You rise from the quiet contemplation of information and radiation, drifting outward into a gentler, more speculative domain. Here, gravity still rules, but the extremes of black hole interiors give way to questions of connection, paths, and possibility. You have explored the inevitability of singularities, the slow whispers of Hawking radiation, and the hidden preservation of information. Now, you consider a universe that might contain bridges, tunnels linking distant regions in ways ordinary intuition cannot imagine. These are wormholes, theoretical structures predicted by the equations of general relativity. They are not science fiction, though they sound fantastical. Mathematically, Einstein and Rosen described them as bridges connecting two distinct points in spacetime. You picture a tunnel, curving through the fabric of the universe, linking regions that might be light years apart, or even connecting entirely separate universes. The image is mesmerizing. Imagine a stretched sheet of paper representing spacetime. Normally, a particle must travel across the surface, following its gentle curves. But a wormhole folds the sheet, bringing distant points close together. A journey that might take millennia along ordinary space could, in principle, traverse in an instant through the wormhole. Yet there is caution. Equations permit their existence, but stability is another question. Most wormhole solutions collapse almost instantly, pinching off before anything could pass through. They are fragile structures, requiring exotic matter with negative energy density to hold them open. And negative energy is not abundant. It is, in some sense, the rarest of cosmic resources, a delicate whisper of possibility rather than a tangible material you could gather. You imagine the consequences of traversable wormholes. The mind stretches to consider time travel, shortcuts across galaxies, even glimpses of parallel realities. And yet, the universe may not allow such luxuries. The physics hints at possibility, but does not grant permission. Imagination and equations meet at the boundary, a subtle place where you can dream of bridges, but never assume they exist. You think about the geometry of a wormhole. One side opens to familiar space. The tunnel curves inward, narrowing and bending, before opening again somewhere distant. The shape is elegant, almost poetic, a handle-like throat connecting two mouths, a pathway carved through spacetime. You imagine traveling along it, surrounded by walls that shimmer with the curvature of gravity itself. Even as you envision the journey, you recognize the dangers. Tidal forces within a wormhole could stretch matter in unpredictable ways. Radiation might fill the tunnel. Exotic matter may be necessary just to prevent collapse. The beauty is theoretical, the risk is extreme. The universe permits the idea, yet guards it jealously. You pause to consider time within a wormhole. Unlike black holes, where time points inward toward a singularity, wormholes could, under certain conditions, distort time in strange ways. Paths that appear short spatially might stretch or compress temporally. You imagine that traveling through a wormhole could move you not just across space, but, subtly, through time itself, though not in ways simple stories of time travel might suggest. And yet, despite the unknowns, there is inspiration. Wormholes represent the meeting of human imagination and precise mathematics. They show that the universe allows questions that stretch beyond daily experience, yet remains bound by logical consistency. You feel a quiet thrill, the same you felt when contemplating singularities, tidal forces, or quantum fluctuations, a sense that reality is more flexible, more astonishing, than you usually perceive. You consider the broader implications. If wormholes could exist, if the equations are more than abstract symbols, then the cosmos may contain shortcuts, hidden connections, unseen links. Perhaps galaxies are closer than they appear, not in space but in the hidden folds of spacetime. Perhaps information can traverse in ways ordinary observation cannot capture. The universe becomes a landscape of subtle possibilities, limited not by fantasy, but by the precise rules it enforces. Yet caution hums in the background. Exotic matter is rare. Instability is pervasive. Most wormholes pinch off before a particle can cross. They are delicate, like dewdrops on a spider's web. The mathematics allows them to form, the cosmos may prevent them from persisting. Here lies the tension between theory and reality, between what can exist in imagination and what can exist in material form. You think of Einstein-Rosen bridges, the original conception of wormholes. They were designed to connect distant regions of space mathematically, not to serve as highways for travelers. The notion of traversability came later, with the recognition that maintaining such a structure requires conditions that may be impossible to achieve naturally. The physics is subtle, precise, unforgiving, yet inspiring. As you drift, you notice a quiet lesson: the universe has boundaries, but within those boundaries lies astonishing flexibility. Equations allow more than observation immediately confirms. Thought experiments become laboratories. Imagination becomes a tool for understanding. You realize that science often moves along this line between what is and what could be, constrained by logic, evidence, and principle. And you feel the gentle tension of speculation. Wormholes are not monsters or portals in the cinematic sense. They are possibilities carved into the mathematics, hints of what spacetime could permit if conditions were just right. They invite exploration without promising arrival. They balance wonder with rigor, curiosity with discipline. You imagine the view from the mouth of a wormhole, ordinary space, with stars and galaxies beyond. You peer through the tunnel and see a different region of the universe, perhaps entirely unfamiliar. Light curves strangely along the throat, distant objects appear shifted, colors stretched and warped. You sense a bridge through the cosmos, delicate, precise, yet utterly theoretical. Even the idea of traversing a wormhole becomes a meditation on physics itself. It reminds you of the balance of forces, the curvature of spacetime, and the limits imposed by energy conditions. Gravity bends, space folds, equations permit, but nature maintains consistency. Possibility dances at the edge of reality, always constrained by the universe's own rules. You reflect on what this teaches about scientific thinking. Curiosity is essential, but imagination must respect law. Wonder must be accompanied by rigor. You cannot claim certainty where equations cannot fully confirm. Wormholes show that science is not about abandoning logic for fantasy, but about exploring the far edges of what is physically allowed, even if it is not observed. You pause at the edge of the wormhole's throat in thought, letting the idea resonate. There is beauty in theoretical structures, elegance in equations that describe what could exist. You feel a subtle connection to all that has come before in your journey, from gravity's pull to the singularity, from tidal stretching to quantum radiation, and now to the bridges that might, in principle, connect distant regions of space. And somewhere at the far end of this speculation, you glimpse the boundary of knowledge. Wormholes remind you that not everything is known, not everything is accessible, but the universe allows the mind to explore, carefully, thoughtfully, rigorously. Possibility exists at the intersection of imagination and mathematics. You drift back from the edge, letting the tunnels fade from your immediate perception, yet carrying their lesson with you. The cosmos is vast, extreme, and sometimes subtle beyond measure. It permits structures that challenge intuition, yet all obey the laws it enforces. Every extreme you have observed, singularities, tidal forces, radiation, now meets the speculative elegance of wormholes. And in the quiet that follows, you feel the next question forming, gentle and compelling: if bridges through spacetime exist in principle, how might black holes themselves connect with the wider cosmos? Could the extreme curvature, the event horizons, the radiation, hint at more subtle paths yet to be discovered? You leave the speculative edge of wormholes and thought experiments, drifting back into the tangible universe. The mathematics, the quantum possibilities, the quiet whisper of information, all are fascinating, but now you return to what we can observe. Black holes, once purely theoretical, now announce themselves through evidence, signals, and subtle traces across the cosmos. You imagine telescopes tuned to detect the invisible. Light does not escape a black hole, yet its presence is revealed by what it affects around it. Stars orbit an unseen center. Gas spirals inward, heated to incredible temperatures, glowing in X-rays and radio waves. The cosmos provides hints, subtle, patient, and precise, that point to these extraordinary objects. You recall the Event Horizon Telescope, a network of observatories spanning the globe. Through careful coordination, it captured an image of a black hole for the first time, a dark circle surrounded by a ring of glowing plasma. You imagine yourself floating at the edge, peering at this shadow. The image is both simple and profound, a visual confirmation of the invisible, a direct glimpse at a region once beyond reach. You feel the immensity of what this reveals. It is not a painting or a simulation, it is a measurement. Light bent by gravity, captured by sensors across continents, combined into a single image. Science has reached across space and time to observe a region where gravity dominates completely. The black hole is no longer just a concept, it exists, observed and measured, in the fabric of reality. You listen for the echoes of black holes, carried through spacetime itself. Gravitational waves ripple outward when black holes merge, stretching and squeezing the very distances between points in the universe. You imagine these waves reaching Earth, imperceptibly altering the space between particles and detectors designed to feel the tiniest distortions. LIGO and Virgo observatories built with painstaking precision record these signals. Each detection tells a story: two massive objects spiraled, collided, and merged, sending ripples outward at the speed of light. You feel the rhythm of these cosmic events. Each merging black hole sings a song of spacetime. The notes are faint, stretching across millions of light-years, yet detectable with patience, ingenuity, and sophisticated instruments. The universe hums quietly, its gravity echoing the motions of these titanic objects. You reflect on the scale. Some black holes contain billions of times the mass of our Sun. Others are smaller, stellar remnants of long-dead stars. Each interacts with its environment in subtle ways, shaping galaxies, influencing star formation, and bending light from distant objects. They are not isolated anomalies but participants in the cosmic narrative, both destructive and creative. You imagine orbiting a black hole safely at a distance. Light bends around you, background stars curve, colors shift. You perceive the effect of gravity directly, the same geometry you explored in theory now observable. Tidal forces stretch but remain mild here. You feel a sense of awe, the universe demonstrating principles you once only imagined, now revealed in real-time observation. You consider the spectrum of black holes. Some quietly consume matter, leaving only a faint glow. Others erupt dramatically, emitting powerful jets of energy that travel thousands of light years. Active galactic nuclei, quasars, and blazars showcase these extremes. Gravity bends, accretion flows, magnetic fields twist, and particles accelerate to near-light speeds. These phenomena, violent yet measured, are signatures of black holes' tangible influence. Even merging black holes, far away, provide stories. You sense the colliding spacetime ripples, the immense energy carried in gravitational waves. Matter may not escape the singularities, but energy in the form of spacetime's own oscillation reaches distant observers. The universe communicates through these subtle vibrations, connecting far-flung regions in ways you can detect if you listen carefully. You reflect on the precision required to detect these signals. A passing gravitational wave changes the distance between mirrors by a fraction of the width of a proton. Yet in that minuscule fluctuation lies information about masses, spins, and even the orientation of distant black holes. You feel the elegance of the universe in this, enormous forces distilled into measurable, delicate patterns. And yet, even with all these observations, mystery persists. The singularity remains hidden. The interiors of black holes cannot be observed directly. Hawking radiation, though predicted, is too faint to detect in most cases. You realize that black holes occupy a paradoxical role. They are both known and unknown, observed and inaccessible, violent and gentle in their signatures. You imagine astronomers charting their orbits, recording emissions, and simulating mergers. Models confirm predictions, yet anomalies always appear. Unexpected behavior in accretion disks, unusual gravitational wave patterns, or strange energy emissions remind us that the universe remains inventive, refusing to be fully captured by theory alone. You feel a sense of humility. Observation provides certainty, yet it also amplifies questions. Each new detection, an image, a wave, a jet opens doors to further inquiry. The black hole is simultaneously understood and mysterious. You sense the dialogue between theory and evidence, the patient negotiation between prediction and measurement. And in this quiet reflection, you perceive the scale of connection. Observing black holes is not merely about watching a distant object, it is about understanding how spacetime itself behaves under extremes, how gravity, quantum physics, and motion intersect, and how the cosmos maintains order even in regions that defy direct perception. You ponder the future. More images will come, more gravitational waves detected. New instruments, more sensitive, more precise, will reveal subtle effects previously invisible. Perhaps Hawking radiation will be observed. Perhaps deviations from predictions will hint at deeper layers of reality. Observation is an ongoing journey, and black holes remain central guides. You feel the gentle continuity between what you imagined and what is measured. The singularities, tidal forces, and information paradoxes you explored are not just thought experiments. They are properties of real objects, observable through careful measurement. Reality validates the abstractions, even while leaving some questions unanswered. You visualize the cosmic symphony. Galaxies swirl around central black holes. Stars orbit, gas falls in, light bends, waves ripple outward. Everything is interconnected, each black hole a note in the vast composition of the universe. You feel attuned to this rhythm, sensing both the power and the subtlety of gravitational influence across unimaginable distances. Even the first black hole ever discovered, Cygnus X1, whispers its story through X-rays. Observations decades old now connect with modern instruments, creating a continuum of knowledge spanning generations. You sense the patient accumulation of evidence, the meticulous piecing together of phenomena, until abstract theory and observable reality meet. And yet, you recognize the humility inherent in observation. For all the data, images, and waves, the interiors of black holes, the singularities, the deepest interactions, remain inaccessible. Mystery persists. Physics admits its limits. Observation, no matter how precise, cannot capture every secret. And perhaps that is as it should be, a reminder that even in the known, wonder endures. You float in this awareness, between certainty and curiosity. Black holes are real, measurable, and profoundly influential, yet they retain secrets. The universe, vast and ancient, has mechanisms beyond direct perception. And as you reflect on these truths, you sense the gentle transition to the next layer of understanding, the broader implications of black holes on knowledge itself, on what we can learn, and on how the cosmos teaches humility, patience, and awe. In this quiet, observational space, you prepare to drift further, not inward, toward the singularity, nor outward, towards speculative bridges, but inward again in reflection. How do these extreme objects shape not only galaxies, but understanding itself? How do they illuminate the limits and beauty of knowledge? And there, on the edge of comprehension, you sense the next chapter whispering, beyond observation, beyond measurement, lies the horizon of understanding itself, a place where gravity teaches not just physics, but perspective. The story continues. You drift back from the concrete observations of black holes, from images captured by telescopes and the subtle vibrations of gravitational waves, into a quieter, reflective space. Here, you are not measuring or calculating. Here, you are contemplating. You feel the weight of all that you have seen, all that you have imagined, and all that you have yet to understand. Black holes are extraordinary teachers. They reveal the extremes of physics, but more than that, they reveal the limits of human understanding. You sense that the universe is neither fully knowable nor fully mysterious. It exists in a delicate balance, a vast continuum where knowledge stretches outward even as questions remain. You consider humility. The singularity, the horizon, the immense curvature of spacetime, these are not simply challenges of measurement. They are reminders that the universe contains realities that surpass everyday experience, that can only be approached with patience, careful thought, and respect. Even our most sophisticated instruments can capture only part of the story. There is a grandeur in this restraint, a beauty in admitting the boundaries of comprehension. And yet, within these limits, curiosity thrives. You feel the gentle pull to continue exploring, to ask questions about information, Hawking radiation, wormholes, and gravitational echoes. Each chapter of your journey has shown you a principle of the cosmos, a lesson in the subtle interplay of forces, matter, and energy. Every observation, every theoretical exploration, deepens not just understanding, but wonder. Black holes teach patience. The processes within and around them unfold over eons. Stars collapse over millions of years. Singularities grow and merge over cosmic time. Hawking radiation leaks energy across spans far longer than human history. You sense the scale of time, stretching your perception, inviting you to contemplate events far beyond the immediacy of your daily life. And there is beauty in that patience. You feel the rhythm of the universe, slow, deliberate, elegant. You realize that understanding is not a race but a gentle journey. Some truths emerge quickly, others only across spans of imagination, observation, and reflection. Black holes, silent and distant, teach that comprehension itself is an unfolding process, like light slowly bending around their immense gravity. You feel a strange intimacy with the cosmos. Though black holes are massive and distant, their existence touches everything: galaxies, stars, spacetime itself. You sense that by understanding them, you participate in the universe's quiet dialogue. Gravity, once a distant concept, becomes a teacher, offering lessons in persistence, balance, and subtlety. You feel connected to these extreme objects, not as conqueror or observer, but as a participant in the cosmic story. You reflect on unanswered questions. The information paradox, the nature of singularities, the potential existence of wormholes, each reminds you that science is not about certainty alone. It is about the patient pursuit of knowledge, tempered by the recognition that some mysteries may endure. You sense that there is grace in leaving questions unresolved, allowing curiosity to persist, even as understanding deepens. And yet, you see how far we have come. From purely theoretical constructs to observations with telescopes and gravitational wave detectors, black holes have moved from abstraction to reality. You feel the delicate balance between theory and evidence, imagination and measurement. The universe has revealed some secrets, yet has retained others, a subtle interplay that encourages both humility and awe. You feel a sense of reflection upon reflection. Each concept explored, the event horizon, spaghettification, Hawking radiation, represents both knowledge and mystery. The universe offers insight, but never surrendering all at once. Black holes are, in a sense, mirrors. They show the extremes of physical law, but also the limits of perception and cognition. They invite you to contemplate not only physics, but the process of understanding itself. You imagine floating outside a supermassive black hole at the center of a distant galaxy. You feel the slow pull of gravity, the bending of light around the horizon, the subtle whispers of radiation escaping into space. Everything seems calm, yet immense. Time stretches and curves around you. You sense both the vastness and the intimacy of the universe, simultaneously overwhelming and deeply personal. And you realize that black holes teach more than physics, they teach perspective. They remind you that life, like the cosmos, is composed of extremes and subtleties, of certainty and mystery, of observable phenomena and hidden truths. They are guides, not threats, showing that even the most powerful forces operate with order and restraint. You ponder the human endeavor itself. We reach outward with telescopes, equations, and thought experiments. We probe what cannot be touched, observe what cannot be seen directly, and imagine what cannot yet exist. Black holes are partners in this journey, silent but profound. They reward patience, precision, and imagination, revealing that understanding is not possession, but participation. You sense a deep continuity. From the collapse of a dying star to the gentle evaporation through Hawking radiation, from the preservation of information to speculative wormholes, each chapter has been a meditation on the cosmos. Each teaches that extremes, mass, gravity, time, space exist alongside subtlety, persistence, and delicate order. And in this duality, you feel a profound sense of connection. Even now, you drift, contemplating the unknown. Singularities remain hidden, information whispers through radiation, and wormholes linger as theoretical possibilities. Yet all these mysteries are framed by law, by principle, by the quiet elegance of physics. The universe, though vast and complex, is intelligible, approachable through careful thought and reflective observation. You feel a gentle surrender, a release into this understanding. There is comfort in acknowledging what cannot yet be fully known. There is wonder in the questions themselves. You perceive that the cosmos does not demand certainty, it invites exploration. Curiosity is the pathway, observation the companion, and reflection the guide. And you notice the rhythm of the universe in your own mind. Gravity curves, matter moves, light bends, and time stretches. The extremes you have witnessed, black holes, tidal forces, quantum fluctuations, exist within a continuum of law and structure. You sense a vast cosmic dance, moving slowly, elegantly, and without hurry. And as you drift toward rest, you carry this understanding with you, that black holes, in their mystery and power, teach patience, humility, and the beauty of unanswered questions. They show that the universe is vast, yet intimately connected, and that even the darkest, most extreme objects participate in the subtle continuity of existence. And then you feel it, a gentle question forming at the edge of thought, soft and insistent. Beyond the horizons of observation, beyond the boundaries of equations, beyond the limits of imagination, what else waits in the folds of spacetime, patiently, silently, awaiting to be discovered? You let the question linger as you close your eyes, allowing your mind to drift along the gentle curvature of understanding, and the universe hums quietly in response. The story ends, for now.